When we solve radical equations, there's a couple of properties of exponents that we have to remember. And I wrote them up here. There's one right here, and it's basically one of the power rules. And there's another one over here that's kind of like the one rule. I just call it the one rule of exponents. But really what this is if I have a number that's raised to a fractional exponent, so it's raised to some fraction, I can take the denominator of that fraction, put it out front, put it over a radical, and then have the original base raised to the power of the numerator. And that sounds like a whole lot, but really this is what it looks like right here. If I have x to the 2/3, that's the same thing as the third root or the cube root of x squared. And the other property is any number raised to the power of 1 is just that number. So if I have x to the 1, that's just x. We don't have to write x to the 1 every time. A million to the power of 1, that's just a million. So with those out of the way, let's go ahead and let's look at these. There's two basic steps when we solve radical equations. We want to isolate the radical, and then any solutions that we may get. We could get none, 1, 2, any solutions that we get. We want to go back into the original equation and check those, okay? And I'll go into a little more detail on why we do that. But for now, let's take these two steps and get going with these. So we want to isolate this radical. Just like when you first learn linear equations, if you had, x plus 2, that's an x, x plus 2 equals 10, you wanted to isolate the x because that's what we were solving for. Now it's the same idea, but we're solving for, think of it as like the variable inside. That x is kind of trapped under this radical. That's why we're isolating the entire radical, and then we can deal with it afterwards. So for that, anything that's not the radical is going to be shipped over to the other side. So we end up with the square root of x minus 1, and we have to subtract that 2 from both sides, and this side will just become an 8 because we do minus 2. Okay, so we're looking good. We've isolated the radical. Now what do we do? Remember, the square root is the same thing as x to the 1/2. So if I have something, the square root of something, I can write that as x to the 1/2. Now we want to get rid of that. And if you remember, we do the opposite operation if we want to get rid of something. So for these, this is where it comes into play. The power rule, the other power rule, the main power rule, if you have an exponent raised to another exponent, they're multiplied. So what do I need to multiply to get rid of this 1/2? And what you do is, no matter what the root is, if it's a fraction, if you want to get rid of that fraction in an exponent, you raise it to the reciprocal. So in this case, we would raise it to 2/1, which is just 2. So we would, and look at that, we square it. So we would square both sides, and when we do that, we would just get the x. So in this case, we would square both sides, square, and it's horrible handwriting, I apologize for that. We would square both sides, and now we're just left with the radicand, whatever's underneath that radical. We've kind of freed it from the square root by squaring it. It just canceled that out, and the other side becomes just a 64. And now this looks pretty nice and straightforward. We just add 1 to both sides, and we get 65. So while you're tempted to say, all right, good, all that work, we got 65, I'm done, you have to go back and double check in this original equation. And let me get rid of this minus 2. So the original equation is this in blue right up here. Let's double check the 65. So the square root of 65 minus 1 is just 64. So the square root of 64 plus 2 equals 10. Let's see if this is true. The square root of 64 is 8. 8 plus 2, that is 10. And there we go. So that would be the solution to this radical equation. And that's it in a nutshell. We can obviously make these a little bit more tricky with more steps, but that's the main idea. We want to isolate the radical, and any solutions that we get after we solve for whatever variable, usually an x, we want to go back and double check in the original because we can get what are called extraneous solutions, which are basically we solved, we got something, we got a value, but it doesn't actually satisfy the original equation. Okay. And I'll write that back up at the top, extraneous solutions. But with this one, let's take a look. We got a little bit more to work with here, but it's the same idea. And look at this. This radical is already isolated, so that's perfect right there. What we need to do is, how do we get rid of this square root? It's just a regular square root. Think of it as whatever is underneath it, the radicand, all raised to the power of 1/2. So to get rid of that, we just square it. And we're going to square the other side. And because we squared a square root, we're just left with whatever's underneath it. So 3x plus 13. This right here, use your FOIL method. We would get x plus 1 times x plus 1. If you're not comfortable with the FOIL method, we have a video on that. I highly suggest you go back because that's very important moving forward. Just like all of these with the quadratics and factoring and all that, you can see how we're building and building and building towards more progressive material. So with this, when we factor it out, or excuse me, when we FOIL it out, when we multiply it out, we'll get an x squared plus 2x plus 1. So we're looking pretty good, but again, we're solving for x. So let's go ahead and let's bring this to the right side so we can get the x squared and keep it positive. And we'll get x squared minus x minus 12 equals 0. Okay, so we're looking good. And if you remember, can we factor this? Do we need to use the quadratic formula? What can we do with this? So take a second and see how we can factor this. And hopefully you thought, we can factor those. The two numbers that multiply to give me negative 12 and add to give me this negative 1, we get x minus 4 and x plus 3. All still equal to 0. So when we solve both of these binomials, we get x equals 4 and x equals negative 3. If you're not sure how I got those, go back and double check on how we solve quadratic equations by factoring. Okay, but now that we've got them in binomial form, we basically just set each of these equal to 0 and figure out what our variable is. So x equals 4, x equals negative 3. And again, you're tempted to think, all right, I'm good, we're done. But you've got to go back and double check in the original formula and see if these actually solve, if they actually work. So with this, let's try the 4. So we get the square root of 3 times 4, because this one right up here. So 3 times 4, so 12 plus 13. So 12 plus 13 gives us what? Or excuse me, 3 times 4. So 12 plus 13 gives us a 25. Now is that equal to x plus 1? So what is x plus 1? X plus 1, and again, it doesn't really help that I have all this stuff over here. I probably should have wrote that in a separate step, but there we go. That's the original equation that we have. So with that, that's where I got the 25 from. 3 times 4 plus 13. And then the other side is just 4 plus 1. We get a 5. And the square root of 25 is 5. And there we go. So x equals 4. That checks out. Now let's try the same thing for negative 3. We get negative 3 times 3, which is negative 9 plus 13 equals negative 3 plus 1. So negative 9 plus 13 gives us a what? That gives us a 4. Negative 3 plus 1 gives us a what? Gives us a negative 2. So we end up with 2 equals negative 2. That is not true. So we get I want to say a false equality. I can't think of the proper term, but something we get a equality statement that's not true. That's what I meant to say. An equality statement that's not true. You obviously know this isn't true. So x equals negative 3 does not work. That's called an extraneous solution. Extraneous, and I'm just going to substitute sullen solution. You've probably seen this before somewhere, but extraneous solution. So it's something that it solves for what we did for this when we squared both sides. We created something a little bit different. We squared the distance. We changed it up a little bit. So while this negative 3 solves this equation right here, it doesn't actually solve this one up here because we squared. So when we squared, although I'm saying square a lot, when we squared both sides, we changed it up a little bit. Although it doesn't, numerically, we didn't change the equation because we did the same thing to both sides, but we can't take that negative value right there. Not because it's negative, but just because that one right there it doesn't solve the original, okay? So that's an extraneous solution. You'll get these two and you have to double check. You have to. Again, I always advocate that you go back and check everything, but with radical equations, you have to go back and check because you'll get two nice looking solutions like this, but one of them could be wrong, okay? And really, all that we've done so far with these two examples that I've showed you have used the square root. All of them have been the square root, but it doesn't have to be just the square root. We can easily use the cube root, the 5th root, the 10th root, although you can obviously see why it gets a lot harder to solve those actual ones. But we could easily do, if I gave you a simpler one like, the cube root of x equals 2. Instead of, we can't square this, right? If you remember, this is the same thing. This cube root of x, that's the same thing as x to the 1/3. How do we get rid of that 1/3? We raise it to the reciprocal, so 3 over 1, and that would just be x to the 1st. Because the power rule, 1/3, if it's an exponent raised to another exponent, we multiply the two exponents. 1/3 times 3 is just 1, and x to the 1 is just x. And this applies to anything. If I had if it was x minus 1 cubed equals 2, it'd be the same idea. We would just cube both sides, and we get x minus 1 equals 8. And then x equals 9. We can go back and plug that in and double check and make sure that we got it. Is the cube root of x minus 1 equal to 2 when x equals 9? That's a 9 down here. So we get 9 minus 1, that's 8. The cube root of 8 is 2 because 2 times 2 times 2 equals 8. And there we go. So I wanted to show you, I know the two examples that we had done so far were only the square root, but we can easily use the cube root. So with that, we'll take it one step further. And these are usually the trickiest of the bunch. I probably shouldn't have prefaced it that because you're going to think, oh, great. But with this, you see a radical on both sides. But in this case, we have a radical with an extra term. So how do we solve that? We do the exact same thing that we've been doing. We've already got a radical that's isolated, so we'll just go about our business like usual. So we're going to square root both sides. So we'll square both sides, and this side just becomes an x plus 4 because the radicals cancel out. On this right side, we're going to FOIL these two out because this is just 1 minus the square root of x plus 2 times itself. So if you're not comfortable with how we FOIL that, then I highly suggest you go back and check out your FOILing methods. But 1 minus the square root of x plus 2, I'll go ahead and rewrite that and get rid of this squared right here. This is the same thing as it times itself. And so we get, if we FOIL this out, we get 1 minus the square root of x plus 2 minus another square root of x plus 2. So that should be minus 2 square root of x plus 2. And then minus x plus 2 root, excuse me, minus square root of x plus 2 times minus square root of x plus 2. That become a positive. And then the square roots cancel each other out. Because we're multiplying the square root of the same thing, it cancels out the square roots. And we would just get plus x plus 2. So now we're looking a lot better than this up here, the original. And I'll write the original square root of x plus 4. Yeah, that's a horrible square root. Equals 1 minus the square root of x plus 2. So with this is a lot easier than this because we only have one radical now. And that's perfect. That's exactly what we wanted to do, is get rid of one of the radicals. So now let's simplify this. Let's get rid of what we can. Let's isolate this, right? So let's get rid of, this is 1 plus 2. There's a positive 3 on the right side. Let's bring that over to the left side by subtracting. Let's bring this positive x over as well. The x's cancel out. The 4 minus 3 becomes a 1. And we get 1 equals negative 2 square root of x plus 2. So now let's isolate it even further. Let's get rid of this coefficient of negative 2 by dividing. And we will get negative 1/2 equals the square root of x plus 2. Now it's looking exactly like the first one that I gave you with different numbers. But what we do is we just square it now. So we square both sides. Square both sides. And what do we get? We get positive 1/4 equals, that's a 4, positive 1/4 equals x plus 2. And then we solve for x. We get x equals negative 7/4. So we did this. We've got this solution, but again, we don't just say, all right, I'm calling it, we're done for the day, right? We have to go back and double check and make sure it is either a actual solution or if it's an extraneous solution. So let's plug it back in up here and see what we get. So let's try a different color. Let's say we got that. So down here, we'll put square root of negative 7/4 plus 4, all equal to 1 minus the square root of negative 7/4 plus 2. So if you simplify these out, I'm assuming that you're comfortable with fractions. If you're not, then please go back and double check on those. But this will give us a square root of 9/4 equals 1 minus the square root of what? What does this give us? That gives us a 1/4. So if we simplify these even further, simplify these radicals, we get 3/2 equals 1 minus, what's the square root of 1/4? That's 1/2. So 1 minus 1/2, we get 1/2. This is definitely not true. So that's not right. This is an extraneous solution. I'm just going to put extraneous solution. So this doesn't actually, there's no solutions to this equation up here. And what that looks like graphically, it would be something like, you haven't graphed these yet, but it would look, one would be like this, one would be like down here somewhere. And they would never intersect. That's what this means. This equation equals this equation. We want to know what x value does that happen? Where do these intersect at? But these never intersect, aka we get something like this where it doesn't make sense because they don't intersect. We're trying to solve it like they do, but they don't in reality. So with all these, I wanted to show you we didn't go too in depth with one particular case. I wanted to show you all the main ones that you will see, the main ideas behind them. You'll start off with the easier ones where you just learn how to, you just learn what this is. You isolate the radical, check your solutions, and you go a little bit deeper, You put radicals on both sides, then you put radicals on both sides where there's an extra term, like that very last one that we just did. And it's the same idea. You want to isolate the radical, Sometimes you have to do it a couple of times. And then any solutions that you get, I'm going to keep saying this, any solutions that you get, you have to go back and check them, because when we square both sides, we're changing a little bit of the distance that's happening. So we're kind of introducing the possibility of extraneous solutions. That's why we have to go back and double check all these with all that extra work. But the idea behind these it's very much the same for any particular one that we get. Sometimes they're a little easier, sometimes they're harder, but the process is the same. Okay, so don't let these radicals, and when you first see them, they're like, oh, what? But it's really not too bad once you get the idea. Okay, and again, you have to be comfortable with your exponent rules. You have to be comfortable with fractions, because they will throw those in there. And but the main idea is your exponent rules and your factoring, quadratics, as well as your FOIL method. Okay, so you can go back and double check yourself. So I hope you found this video helpful. If you have any questions or comments, please leave them below. And until next time, this is Justin with Top Tier Math.